So welcome back to Honors Pre-Calculus Review and Preview. This is our second and final day doing this. Yesterday we reviewed Algebra 2 and started a little bit of pre-calculus by talking about functions and polynomial functions and rational functions. Today we're going to continue by talking about exponential and logarithmic functions and then trigonometric functions and finally some advanced trigonometry. If we have time at the end, we'll go more in depth and talk about a bit more of pre-calculus, maybe limits, which are a big part of pre-calculus and then a big part of calculus as well. So let's get started. First things first, exponential and logarithmic functions. We talked about exponents a little bit yesterday when we were talking about polynomials, but basically what an exponent is basically repeated multiplication. Now, an exponential function is not going to be something like x to the power of 2. Instead, it's going to be 2 to the power of x. X is in the exponent, which is why it's called exponential function. And we said function notation was f of x equals. So an exponential function would look something like this. How do you graph an exponential function? Well, an exponential function, first locate the horizontal asymptote. We talked about horizontal asymptotes last time. Basically, it's a line that is never reached but is approached by a graph. And sometimes it could be crossed over. Vertical asymptotes, on the other hand, cannot be crossed over. Horizontal ones could in some cases, but in most rational functions and exponential functions, you would not cross over, especially in exponential functions. So in this case, the horizontal asymptote is 0. It would be whatever you add here. So if it's plus 1, then the horizontal asymptote would be 1. However, since our function didn't have anything there, the horizontal asymptote is just 0. So if I were to draw a rough dotted line there, you would see that the horizontal asymptote is there. Next, you want to pick one point, most likely going to be the center in air quotes. It's not actually the center, but it is an important point. It's usually going to be on the y-axis. It's going to be the y-intercept, but it doesn't have to be. In some cases, it's not. If it was something like to the power of x minus 2, it would not be the y-intercept, but in this case, it would be. Basically, we would plug in 0. Whatever makes this exponent 0 is what we would plug in. So in this case, since it's just x, we plug in 0, which is the y-axis. We plug in 0, we get 1, and that would be this point right here. Now, based on what this is, we calculate a new point. So since this is 2, you would plug in x equals 1. When you plug in that, you get 2. And then you know that it has to go down towards the horizontal asymptote in this direction and up in the other direction, and you'll get your exponential graph. How would you know which direction to draw it? Well, if it's a number between greater than 1, then it would be going like that or like that. Basically, it would be getting larger. The magnitude of the values would be getting larger over time. But if it's between 0 and 1, it would be slowly decreasing over time. Those are exponential functions in a nutshell. Moving on to logarithmic functions. So we talked about inverse functions a little bit last time. So the logarithm is the inverse of the exponent. When you have log base b of x equals a, for instance, this is equal to saying b to the power of a equals x. Let me give you an example. Let's say it's base 2 and x is 8. What would a be? So you're basically saying log base 2 of 8 equals, and that's a pretty fair logarithmic question. We convert that into exponents. We say 2 to what power, 2 to the power of a, is equal to 8. And then you look back and you say, oh, it's 3. A has to be 3. And that would be your answer. Log base 2 of 8 is 3. Now, How would we graph a logarithmic function? Just as you would graph an inverse function. One thing we didn't mention last time is that to graph an inverse function, you basically reflect the original function over the line y equals x. So this is the line y equals x. If I had a function like this, for instance, the reflection would be this, and that would be the inverse function. Note that this is not even a function because it fails the vertical line test, but just the inverse relation. If it was something like a parabola, then it would look like that as the inverse. This is a function, the parabola, but this is not. So sometimes one can be a function and the other would not be. Sometimes both, neither are functions, sometimes both are functions. So just a recap of inverse functions. Let's apply that here. Let's say we have an exponential function like last time, and this is y equals x. This would be the inverse. You would move every point opposite here. You would get something that looks like that. But how do you accurately graph it? So let's say it's log base 2 of x. First things first, identify the vertical asymptote in this case. It's going to be a similar procedure. It's going to be 0 in this case since there is nothing. If it was something like x minus 5, then the vertical asymptote would be 5. But since it's just x, it's 0. Next, locate the point that's the central point again. In this case, when you plug in 0 as y, what would make it equal to 0? Well, when x is 1, 2 to the power of 0 is 1, so you would plot 0, 1. So you're finding the x-intercept in this case. Now, you use the remaining variables, in this case 2. If there is a number here like 3 here, you would also use that. And you can compress that all into one thing. You just find an additional point, just like we did with exponential functions. So the next point, let's say x is 1. This is x is 1. Let's say x is 2. That means y would be 1. And we'll get that point. Now we just have to connect it. We know it has to not touch, but go down towards this asymptote. And then we know it'll go like that. So that was just the basics of exponential and logarithmic functions. Moving on to trigonometry and trigonometric functions. This one I'm not going to go too deep into. The basic trigonometric functions, sine, cosine, tangent. So sine looks something like this, where the central point or the midline point intersects the y-axis. On the other hand, cosine looks like that, where either the maximum or the minimum intersects the midline point. In this case, the maximum intersects the y-axis, in this case, the maximum does because it's positive cosine. If it was negative cosine, it would go like this, and then minimum would intersect the y-axis. If it was negative sine, it, as you might imagine, would be flipped around like this, and therefore, it's still the central point that intersects the y-axis, but the minimum follows that immediately. You can do transformations to sine and cosine. I'm just going to call it sine for now, but same thing applies to cosine. The basic transformations you can apply, you can multiply by a number. This is the amplitude. It changes the distance up and down of the maximum and minimum. Then I'm just using sine as an example. You can change the period. So this is a value b, and b would be equal to 2 pi over the period, which I'm going to abbreviate with p. So you can change the period, which is basically the length from one maximum to another maximum point. So if you have a graph like this is the period. The amplitude would be the distance from the midline to the maximum, which is also equal to the distance from the midline to the minimum. You can also have a horizontal shift, also known as a phase shift. You basically move it over by h, and then you can have a vertical shift. This determines the y value of the midline. So the midline can increase or decrease depending on this k value. So let's go with an example. Let's say we want to graph the function negative 4 cosine 2 pi times x minus 1 minus 2. How would we graph it? First of all, we know it's cosine, which means either the maximum or the minimum intersects the y-axis. We know it's negative, so it must be the minimum. There's a method called the 5-point method. Basically, we make the sketch. You would learn about it in pre-calculus most likely, but for a previous pre-calculus, we won't use this 5-point method. Instead, we'll just show you how each transformation affects the graph. So if this is regular cosine, I'm actually going to change the scaling a bit to show the changes we've made. So let's say it's something like this. That's regular cosine. Now we have negative cosine, so we basically flip that over and we get something like that. The amplitude is 4. This has an amplitude of 1 generally, so we changed that, which is why I scaled it to make it easier to change the amplitude. The period is 2 pi. Sorry, the b value is 2 pi, and we said the b value is 2 pi over the period, so the period must be 1. So it should actually be even closer together. It's shifted horizontally by 1 unit to the right, even though it's a negative sign, it's to the right. So it's gonna look something like this. Again, this is a rough sketch. I didn't actually calculate values to make a proper sketch. And then the midline is minus 2, so it goes down 2. So this is the midline. The new graph would look something like this. Okay, moving on to the next topic. This lesson would be a bit shorter than the previous one because the main topic we need to cover in this entire session is review of Algebra 2, which we already did. We also went into a bit of pre-calculus last time, so we used up some time to go into, and today we just have a little bit of preview left. So our final topic for the day would be trigonometry. We're basically going to be looking at trigonometric identities and equations. So the main ones you should know are, for example, sine squared x plus cosine squared x equals 1. This is known as the Pythagorean identity, not to be confused with the Pythagorean theorem, but it is named that way because it is related to the Pythagorean theorem. There are variations of this as well, and there are other identities such as tan x is equal to sine x over cosine x. For instance, and these identities will help you solve trigonometric equations. So let's do a trigonometric equation as practice. Let's say it is cosine squared x minus sine squared equals sine x. So this includes properties that we haven't looked into yet, identities that we didn't cover so far. But this is not about learning the identities here and now. It's about learning the process of how to solve an equation given identities. So the identity that we use here is cosine 2x can be rewritten as exactly the left side of this equation. So we replace that, we get cosine 2x is equal to sine x. We can replace this again with another variation of cosine 2x. There are 3 total variations, and this one is 1 minus 2 sine squared x equals sine x. So now we replace sine x with u. This is u substitution, and it's used to make the equation a bit less complicated. So if we replace this here, we get 1 minus 2u squared is equal to u. Now it's just a simple quadratic equation. We can solve for u, and using that we can solve for x by substituting it back and saying u is equal to sine x. So we found u to be 0.5, for example. We would substitute it in and find x based on the value that we get for u. So that's just a brief example. Now that we do have extra time left, I just want to go over limits real quick because it is a very important part of the later half of pre-calculus, and it's a very important part in calculus. So if you're taking pre-calculus, you do want to get a head start on calculus as well. So what is a limit? A limit is basically where you're approaching something. So if I have a function that looks like this, and I want to find the limit as x approaches 2, so this is how you would write it, as x approaches 2 of this function f of x, that would be this point right here. Note that when you're taking the limit of that point, it's different than actually taking the value of the function at that point. And we'll illustrate that in a few examples later, but the function doesn't even have to exist at that point for their limit to exist. Let me show you an example. What if this function that I have just so happens to have a hole here because it's a rational function that has a hole? The reason why it has a hole, we didn't cover that when we were talking about rational functions, but you would learn that in pre-calculus, how to identify if it's a hole, an asymptote, or whatever. If there's a hole at x equals 2 and I want to find the limit as x equals 2, you can't just say it does not exist. It does exist. The limit exists because on both sides it approaches this same point. Even though it's not actually defined as that point, as the function, it's still, the limit still exists. Another example. Let's say it looks something like this. A piecewise function. What would the limit be here? Well, in this case, the limit does not exist. Not because of the fact that there is an empty circle here and a closed circle here, but basically because of the fact that for a limit to exist, both one-sided limits must exist. So the limit from this side, which is where approach is coming from this side, is not equal to the limit coming from this side. That's not fine. We want both sides to exist and be equal to each other. That's the key point. Since they're not equal to each other, you can't just say like, oh, it approaches this because there's a closed circle here. No, they both are being approached, and you can't have two limits, which means the limit does not exist. And another interesting example is if we go back to the whole idea, but the function does exist, just somewhere else. So it's just a jump up there and then continuing back with the rest of the graph. Where would the limit be? No, it's not up here. Even though the function exists there, it's still this whole because that's where the two sides are coming towards. So that's a brief introduction to limits and some of the important characteristics, and just a little bit of algebra with limits. So that was like geometry with limits because it's all about graphs. But there's some limit rules. So let's say it goes to a, we have f of x plus g of x. That's equal to the sum of the separate limits. If we have f of x minus a g of x, or times or divided by, it would be those respective operations as well. So it could be times, it could also be divided by. Just make sure that g of x does not equal to 0, so you have to specify that in the domain. And those are some basic limit laws. You can use that to algebraically determine limits. You might want a graph just in case, because you never know, but when you have a polynomial, you will definitely always have, you can basically just plug in the value into the limit, and you'll get your limit. So if it was limit as x approaches 2 of a polynomial, you can just plug in 2 as x, and that would be your limit. But for other functions, such as rational functions, you would need to do a little bit of investigating to make sure that's what it is. And that's it for this honors pre-calculus review and preview. We went over some other functions as well as trigonometry, and now we briefly touched limits. And that was just a preview of pre-calculus to help you get ready for your next year. So good luck with pre-calculus, and I'll see you then.